So this is going to be a generic update for Skia. Skia is a graphics engine that's used by several projects inside Google. Blink being the most, interesting, certainly within earshot. So some of what I will talk about is going to be very Blink specific, and it will make sense, I hope. And some of it's going to be maybe a little esoteric or far afield, so please bear with me through that part. All right. So Skia is a project, and that's where you can read about it and get the code. It is pulled into Chrome and Blink through the depth mechanism. So you'll see references to that. So here's a quick overview. Skia is just a funny name. It is a 2D graphics engine. It's written to be a portable engine to do sort of general purpose 2D transformations, including perspective. It will draw a variety of graphics primitives, text and geometry and images. And it sort of has a large list of effects that you sort of apply to those primitives. This is sort of how the drawing API is organized, in fact. You have a context, you say the thing you're drawing, the rectangle, the piece of text, the image, the triangle, whatever. And then a bundle of effects, where effects are simple, what color is it, to very complex, here's a giant dag of image filters that Senor Blanco worked on, all for your rectangle. I said it's a portable engine. It runs in many places. It has a porting layer. So we do our best to be self-contained. It's in some sense near the bottom of the stack. If hardware, kernel, stuffing, Skia is somewhere down here, and applications are up higher. So in general, it's written in C++. We have some assembly code as we learn how to write it. But we have sort of configurable backends to do services that Skia itself needs to fulfill its contract, but that are not fundamental to the implementation of Skia. So one is a font backend. So we draw text. We have a lot of code to do that fast. But at the genesis of getting the shape for a character at a size from a font, we sort of have a plug-in mechanism where we will jack into whatever the operating system's service for that is. If it's on the Mac, we call in the core text. If it's on the Windows, Direct Write or GDI, free type and other instances. So that part is a piece of Skia, but it's really not in our code base, right? This is a link time thing that gets resolved. Same with using threads, some low-level primitives. We have thread services. We can operate in multiple threads, et cetera. Obviously, we don't have our own thread package. Same for memory. But this is a pretty close, accurate summary of the parts that are not portable. Plus or minus, the code builds with these few things under the hood, and then you can build on top. When you go to draw something with the primitives and the effects I mentioned, there's a third component of that, and that's what is the backend into which you are drawing. And I tried to break, and Skia has multiple of these, all that present the same drawing API, but you have sort of multiple funnels behind the scenes. So I broke these into 3 categories. One is just pixels, which I call the surface, because we have an API for building a surface. And there are 2 variations for 2 implementations to generate pixels. One uses the CPU, and then we just write into memory. And the other is the GPU, which also generates pixels, but with a very different piece of code, and obviously not in main memory, but directly on the hardware. A second kind of backend is through our document factory. And this is if you're wanting your drawing commands to end up as a target for printing. So via document, you can get a page, or a page, you can get a drawing context called the canvas. And that's the same API you got from a surface. But now when you say draw this, draw that, we transcribe those into PDF or into XPS and stream those out. Third category is where you want to sort of pay me now, pay me later. You want to record your drawing commands, but just we will stash those into a list. And then later you can have this list object, this picture or this pipe, and replay it into another context. And we have two variations, a picture and a pipe. Pipe is obviously gets flushed as it needs to. Okay, and I mentioned some that there are sort of multiple clients within Google and outside of Google using the library. Here are some of them. In the case of Blink, we are sort of most obviously seen as under the hood, under the graphics context hood. Behind that .h file is a layer of graphics context code, but then usually those calls and then turn into making calls to the Skia API. In Chrome, there's at least two kinds of places that the code is used. One is in the UI GFX layer, and a second piece, I guess they're all the same, but a second piece is for the compositor itself. A third interesting client from our perspective is just the Android framework. So when you draw, when Android apps draw, in particular if they draw using software or generating PDFs, the Skia code is also there. And some third parties of note are using the Skia library for their rendering. For today, we're going to really focus on how Skia is used in Blink and how the Skia team is trying to work, learn the Blink code so that it's a two-way street for improvements. One area is in fonts, and I think Emil's going to give a talk in more detail about all the text and font wonders in Blink. Some particular things where Skia comes in the effort to sort of unify and simplify the backends for Blink in terms of font backends. So if Skia has every font backend, Blink's had all those and more. Some of the types in Skia now, the typeface object, the font manager object, are finding their way into Blink as a way to sort of hide that variable backend. So for a lot of the code now in Blink, you can make a semi-portable looking call, find a typeface from a name or a descriptor set, and use that freely inside Blink and not know if behind the scenes that's direct write or GDI or something. In particular, speaking of direct write and GDI, this system, at the behest of Blink, has a run. Typically, this is a compile time decision. What kind of font backend do we link against? On Windows, we link against both, so that at runtime, Blink can sort of switch our factory when they make a typeface object. Shall it be backed by GDI? Shall it be backed by direct write? And this may happen because of direct write is not available, or this web page, this particular page wants a legacy behavior. So this facility is supported in the Skia API. Text blobs, it's a piece that is sort of originates inside Skia, but was inspired completely by the use case for Blink. And so Florin and others here can give you more details on how that was implemented. I think this was mentioned earlier, as a way to speed up sort of compact areas of text that can be all specified in one lump, as opposed to separate lines at a time. And a current effort right now that we're investigating is trying to simplify / remove much of the decision-making and complexity that's riddled through some of the rendering code in Blink related to turning on LCD text rendering. This is ongoing. Okay, another focus for some of our work in Blink has been record time rasterization, RTR. What I mean by this is when Blink will, during its paint pass, I think it's still called paint or draw rect, as they walk down to try to give primitives to Skia to render, sometimes they will decide to, in fact, do a quick render in that pass and then hand a bitmap to the graphics backend. Much of this is gone, but I'm going to bring it up because it's not all gone. The classic cases in the past have been when Blink decided that an image was going to have to be scaled for the final result, and they had a particular high-quality algorithm they wanted to apply, and or at the time it may have been faster for them to scale it, save a second copy of the image in its scaled form in the Blink tree, and then push that to the rendering engine to render. SVG has been used, had or has several instances of needing to rasterize something because the API in graphics context was not expressive enough to sort of say it directly. Some pattern constructs fell into this, sometimes creating complex masks. To achieve that, they sort of had to draw the mask, capture the bits, and then send that down as a clip or a mask to graphics context. This idea of doing rasterization at that level is sort of problematic for many reasons, not the least of which are to make it high quality, you need to know the exact matrix that you will end up wanting to have scaled that drawing operation to. And even though graphics context has a get CTM call, you can't always trust it. For whatever reason, that may be set to a number, and by the time it gets sent to the screen, some other scale factor may or may not have been applied. Also, as we have evolved the code to know about GPUs versus CPU surfaces, deciding to pre-render into one of those backends may or may not be a match for what the compositor will finally want to do. And often this just takes time. So for all these reasons, there has been a long-running effort, and it's probably nearly done, but still being worked on, to find each place in the code base where we see this particular sin occur and find the solution. So here were some of the solutions that I remember. Maybe the largest, and Senor Blanco, are you in the room? So Stephen spent a lifetime trying to take all of the image filtering code that was rasterizing in the Blink thread and encapsulate that into lightweight DAGs and be able to communicate that in a thread-safe fashion across the border so that that rasterization can both be done out of the WebKit thread and possibly be done entirely on a GPU if that's the target. So this maybe is the largest piece of tricky, cool code that is now available and now sort of can be turned on inside the Blink side. A second really was image scaling, bitmap scaling. In response to this, Skia has expanded the suite of sort of quality levels we have for bitmap scaling as primitives in Skia. We used to just do BiLerp or not lerp. And now we've added bitmaps and we've added fancy, where fancy is sort of compile time defined. And as necessary, caching on top of fancy because it's so slow. So that was able to remove that slice of code where we were both spending time often getting the scale wrong, if just by a tiny bit. So a classic funny bug was Blink scaled an image thinking it knew the CTM. Maybe it rounded the edges to be integral, gave that image to Skia. Skia looked at the resulting matrix and said, wow, it's really close. I just have to do a BiLerp on top of that. So we paid the heavy price and then we filtered it twice. This has now been removed. A very clever use of a modern Skia primitive thrown into Blink has been using sub-pictures, using pictures, but I'll say sub-picture, meaning it locally scoped within part of the render tree, to cache the rendering of just that sub-piece of the tree. And SVG was sort of the first to try this out. They had well-defined boundaries where we're sort of entering, and I'll get the details wrong, entering an SVG image context thing. They would kick on, record a Skia picture, call their children, pop back, and then this is the picture that they handed back to the graphics context as when the larger tree was traversed. And this was able to replace a pre-existing implementation where SVG would rasterize and make big memory expensive bitmaps that they would hand off possibly at the wrong resolution. Masks were another, and so here the technology now being used in some combination is sometimes pictures inside SVG, sometimes where you really do have to render to generate a mask correctly, and I don't remember the details for this, but Florin, who's in the room, can give you details. You can now specify a request to render an off-screen and treat it as a mask as a set of commands into Skia. So while you're still invoking a sidecar rasterization to implement a particular look, we don't have to pay any of that price during the Blink pass. We issue the commands that say, pop off to the side, draw something, treat that as a mask, bang it down, but don't do it now. Do it at playback when you know the resolution, when you know if you're on the GPU or not, etc. Or or when you're going to go to a printer and then the implementation for PostScript is yet different again. So all this tooling in Blink allows what is being spit out to be a little more versatile by the different backends within the browser. And the last, which is especially clever, I think, is to extend Skia's notion of patterns, which for 9 years had been, give me a bitmap and a rule that says you want it repeat tiled or mirror tiled, and extend that to device independent rendering. So we now have a picture shader that does this, so you can describe the original content of your cell in something device independent, and then at playback, we will find the right resolution, do a quick raster, and then tile that with repeat or mirror or clamp, and then cache that in an LRU cache so that if we have to render that again, you get the same speed as if you had given us the raster, but it's always at the right res, and we'll free up that RAM if something more important comes in. So we don't have to sort of keep filling up RAM as we're trying to speed things up. Another area you've been hearing again and again is sort of recording speed and recording features during the pass in Blink. As you know, the graphics context now is almost always backed by a picture recorder and not by direct raster. And this means what it says on screen. We're going to record the commands. To do that well, to do that in a way that we can then hand that result to the compositor or somebody else, which may, we hope, be in a separate thread, we have to sort of be smart about. We have to shallow copy the commands that are cheap, and the things that are expensive, we have to not copy them. So, yes, we'll get to the next slide. So that involves large things, images, embedded fonts. If there's an SVG font or a CSS font object, we want to refer to that, but we don't want to copy it. And again, yes, and it may be that picture has to play it back in the multiple threads. We have to make that recording process fast and sound. To do all that, we had a completely new implementation, a new backend to picture. And Mike Klein, who is not here, is responsible for inspiration for that work, though in the end, his very good idea resulted in a very lot of work for the rest of the team. Because what he said was, let's make shallow copies of everything and just go at the speed of memory. And that's the target, the line in the sand for recording the drawing commands. To do that, we had to make that legal. We had to say everything that's not a rectangle, a color, a line of text has to be something that can be refed so that we share the same memory that Blink has in some safe fashion. For bitmaps and these sorts of Blink provided objects, not so hard. We all just agree. We have a pointer. We promise not to write to it. And Skia has primitives to sort of encapsulate this. This also applied to all of the effects. If you remember earlier, all the effects, including Stephen's great image filter DAGs, all of these which are getting built and subclassed and instanced inside the Blink tree, and this includes not just image filters, gradients, dashing, path effects, blurs, shadows. These are all represented in the Skia API as little subclasses that have virtual methods and private data. To make all of those free to snap out of Blink's thread and then reuse in a different thread, we had to make all of those thread safe. We had to make those immutable and re-entrant safe. And in fact, it ended up being two different efforts, or they piled on top of each other. One was a sort of architectural change in what the API was for building these things. It wasn't too horrible, but very often there was a, yes, make a gradient call. And then we said, oh, would you like to change the matrix behind that gradient? Or did you want to tweak the alpha or change something? Can't really do that in a safe fashion if we're going to need a reliable playback in a different thread. So we had to change APIs, fix up call sites. It's required a fair amount of work on the Android side, which has job APIs exposing Skia since a few years ago, and they had to be retrofitted. We also had to make them re-entrant safe. And this was a second pass through the code where we said, sure, everything is const, except this pointer to this lazy cache that I'm going to build the first time I draw the gradient, or something like that. Or I'll const cast it, save the old alpha, pop the new one in the paint, draw it, restore the alpha. no one will be the wiser until we're drawing in parallel with lots of threads. So we also had an effort to, anyways, there was a lot of effort. But it's done. As far as we know, when you make a picture, you can now take that picture and use that one reft piece of RAM, spawn it on a bunch of threads, each thread rendering it with a different transform to a different render target, and all this draws correctly. And in fact, record time has gone down. I don't know what the number is, but I think it's lots faster. There's always room to get better, but just architecturally, it does so much less work. It got faster. After recording comes playback. So Skia has a number of efforts and a number of tricks that have landed to try to speed up the playing of pictures. Once they've been popped out of Blink, now we have to rasterize them. One is just plain old people optimizations. I don't have samples in the slide deck, but we have a sort of classic, list of shame, wall of shame back in the office where we say, yeah, have you seen this pattern come out of Blink? And it, classic ones that we all chortle over are, save, concat, clip rec, save, restore, restore, restore. Or where nothing got drawn, but a whole lot of state got pushed and then popped. Or another terrible one is we see a save layer. This is that command that says, I'm going to do temporary off-screen rendering and then pop it back. Save layer, draw one thing with just an alpha and then restore. Anyway, so obviously this is a double draw. We have a people optimization step that happens after recording. The particular peoples get enabled basically what day of the week is it, because we're trying to figure out what the cost between extras checking versus the benefits thereof. But the second one, for instance, gets optimized to turn into just draw that primitive where we mutate the alpha on the paint itself. So instead of drawing it the original alpha to a buffer, crushing the buffer to a different alpha and compositing it, we just change its parameter, we multiply the two alphas, and then let the regular draw call just pass through. So there's no buffer allocation, there's no double draw. Also building hierarchies, building culling information after the fact, as we want to see the sequence of draws that have come in, how many of them overlap, are they grouped together? A classic problem for Skia's performance for general web content is a web page is this big. The rendering target, if it's either the window or a tile, if we're being tiled by the compositor, is much smaller. So Skia spends a lot of time not drawing. So we have optimization passes against the picture where we try to do an analysis so that we can quickly, in some sort of log n time, find all the drawing commands we don't have to execute. Turns out they never draw wrong, but we can spend a lot of time getting in and out of our pipeline only to discover down at the blitter, oh, in fact, this guy's not visible. So we need to do that as sort of at composite levels higher up. We have particular optimizations that are specialized just for the GPU. Again, that can get applied to the pictures in particular, in this second pass before we actually play it back. The catchphrase for the first is called layer hoisting. And so this is something that the software backend, and as Blink grew up using graphics commands, never sort of saw this as being expensive because it wasn't for a software backend until we had a GPU backend, which is this notion of when you do have to do a sidecar render, and we do often for good reasons. On a CPU, right, this is me moving a pointer, and then I do some drawing, and then I move a pointer, and I do some more drawing. Almost no cost other than we have the write through cache. On the GPU, it's like starting your car and pulling out of the driveway and turning it off, and then starting your car and pulling it back into the driveway. If you tell the GPU to render this render target, and then draw very quickly and now come back, this is an enormous state flush for the GPU, terribly slow. But because we see that in line, this is the natural way to describe a lot of compound rendering constructs in the browser. We are now working on a pass that will zip through the picture, find each of those off-screen renders, which are sort of little drawing problems, whose answers then get composited later, hoisting them to the beginning in terms of order of operation, so that on playback, we will now say, all right, let me allocate a bunch of off-screen and do all my sub-renders. Boom, 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 boom. Do one render target swap. Okay, it's a state swap. Boom, to the regular buffer. And now we just pull the answers in and composite them. Big speed win, big depending on the GPU architecture. It turns out NVIDIA doesn't really suffer as much as other kinds of architectures. So as with all things on the GPU, it's never as easy as it should be. But in general, this hoisting is proven to be a great win. And the second is distance field technology, which we apply to fonts and now actually to concave paths in general. And this is just another recognition that for many GPU architectures, relying on multi-sampling in hardware is not always fast enough. So often Skia has to do its own anti-aliasing algorithms per primitive because the hardware is not doing it for us. And that's particularly hard for concave paths because concave is not a word that the GPU guys like to hear. So sometimes small, complex concave shapes like fonts and other paths get rendered in software. And then with this technology, rather than uploading the software rendered mask, which is now valid as a mask for the GPU, until you have a new scale factor, and now of course it's not valid, we have to go back to the CPU and re-render, re-upload mask. Using distance field transformations of the mask, we can create a distance field mask that is usable at a range of zooms. So we can do sort of one upload and reuse that for the same primitives at a range of sizes. And these sort of build in a pyramid, not unlike maps. So this has, I don't know the state of the design. It certainly landed in Skia. I don't know where this is behind flags in Blink. Under development. There's a particular call that isn't different than what I've been describing, but it makes sort of focus a lot of these discussions about multi-passes and hoisting and giving Skia enough context so that we understand what the client is going to do for several things. So there's a new call in Skia called the multi-picture draw. And its API looks something like that. Instead of the classic call in Skia is, I have a canvas, arrow, draw, foo, pass a foo, and a paint. This is the triumvirate of a Skia call. And perhaps there's a previous matrix that was set earlier. Multi-picture draw says, let's just vectorize that. Give me an array of canvases, each one independent. Give me an array of pictures, though they could be the same picture because they're all shareable, an array of optional matrices, and an array of paints. And now say, draw all of it. Now the contract for this call says, I don't get to tell you what order I'm going to execute those because while the matrices can be shared, the paints can be shared, the pictures can be shared, they're all marked const. The canvases are clearly not const. There's nothing more mutable than the Skia canvas. Every call is, push, pop, set the matrix. So you give us a vector, we run off and do it. This is actually landed, I believe, inside the compositor. So here are two examples, though not the only ways to use it. One is you just have one picture, and it's this big, but you plan to render it into multiple tiles. And those are really separate draws because the memory for the tile may or may not be physically separate memory. And each one would require drawing the same large picture, perhaps translated so that the part you're interested in lands in the rectangle of the tile. Maybe there's an additional clip, usually doesn't need that. So rather than sequentially just telling us to do them one at a time, where we may do some setup work for the first, maybe we have to decode an image, we have to compute an off-screen blur, and then we return, and then you tell us to do it again with the same picture. And we say, oh, crap, I was just here a minute ago, and I just had that blur, and the size of the blur actually logically would cover more than one tile. Too bad I didn't know that first time I was around. So this call lets us see all that state up front. So this is implemented, though plenty of sort of long tail of benefits to glean from it. You give us, in this example, give us that one picture and pointers to all the states that you want to pop into different tiles for the same picture. And we can do what I described about layer hoisting. In fact, we hoist more than layers. We can hoist image filter DAG operations. And again, and even atlas those, because many of those produce temporary render targets that later get composed. We can sniff all of that out, and as we have RAM to do it, pre-render all those things before they're needed, so there's no lag in the GPU pipe. And in fact, it's a case of the blur or something that spans multiple tiles. We get the second one for free because we've computed this intermediate image. Maybe the first tile only used a third of it, but the next tile we used the middle third, et cetera. So the atlas can live, the pre-rendered caches can live, in this case, at least as long as the entire call. On top of this, we're looking at adding actual long-term caching of these, because pictures being immutable, they have nice magic IDs. We know how to do an associative cache. I don't think we're doing a lot of caching yet, but we're in position to. A second use case would just be if you have multiple layers that Blink has described that do need to be rendered, and we have some display list for each. We can bang them. We can see them all at once. Now, these don't visually overlap, but they may in turn have shared assets inside the pictures. If we have to pre-decode an image that may be referenced in more than one place, again, the multi-picture draw has scope enough to see this. Oh, sorry, I just told you what this slide has. Yes, read that. CPU. Once in a great while, the compositor still asks us to invoke the software rasterizer. Warms my heart. With multi-picture draw, we are in a natural position. Since I said the rendering order is not specified because each canvas is independent, we can easily, in fact, take advantage of a thread pool and actually render all those in parallel. And this code is up and running. It's not turned on in Blink, but we have experimental code that says, sure enough, when all the stars align, you can drain as much battery as you want all at once, because we can saturate all the cores. The API doesn't require it, but it's sort of, we now have the scope to do it. By the way, the star means more to be implement all the things on my slide in the word optimizations. Okay, that's a lot of what we are currently working on in Blink. Going forward. So we're always thinking about finding new ways to go faster. On the GPU side, here are some of them. OpenGL doesn't stand still. OpenGL ES2 is no longer the only game in town. So Skia is working on finding ways to, again, with the same API at the top, take advantage of extended features on the hardware when they're made available to us, like geometry shaders, tessellation shaders. We are working on, as another kind of optimization, when we look at a picture or multiple pictures, not just doing hoisting, which is a reordering, but doing per individual primitive reordering to increase the batching. And again, like every API, GL wants to sort of see all the data in one call, just like Skia. But often we may see sort of ping-pongy commands coming in from Blink. We may see, draw a piece of text, now draw a rectangle. Now draw a piece of text, now draw a rectangle. Now you see it. Depending on how that is implemented in our GPU backend, that may mean a shader swap, a shader program swap between each primitive. The worst case that I remember from the past was trying to draw Google spreadsheets on the GPU, which rendered about 2 or 3 times slower than software at the time. And this is because every cell of the spreadsheet drew the following. Draw a little rectangle for the left edge. Draw a little rectangle for the top. Wait, save the clip state and push a clip for this little rectangle. Now draw white. That happens to fit exactly in that rectangle. Now draw a little piece of text. Repeat n times m. And this clip pushing and popping between different shader programs, the GPU backend got dizzy and just grind to a halt. This is a classic problem. We are trying to work on classic solutions, which would be an analysis of those commands with bounding box overlaps, Can we reorder that so we turn it into a lot of rectangle draws, a lot of white fills, a lot of text draws without getting it wrong? Ongoing effort. But if you're reordering and batching, this is what we mean. Also, in GL, not only are there sort of higher end APIs that we are learning to take advantage of outside of ES2, like tessellation shaders, et cetera. There's now a wave of new exciting low-level OpenGL APIs. I think there's a new GL, I forgot what the name is, from the spec world. Apple announced Mantle, Metal. So all these are very interesting. They're all different, but we know that space will settle at some point. But they have some interesting things in common, which are a different way to think about managing state if you're a smart client. And Ganesh, our GPU backend, is looking at ways to refactor its code so that we can be efficient clients of regular GL, but also optimal client if there's this other low-level variant where Ganesh does more state management, but perhaps gets a speed win out of this. So this is an ongoing effort in the roadmap. On the CPU side, basically, I mentioned at the very beginning, we have some SIMD code. We have very little SIMD code. We think there's lots of rooms for this, especially now in the float space. We have started experiments to use vectors of 4 floats everywhere. Mostly seems to go faster. And really, culling, we can never get fast enough trying to not draw things. So this is just general purpose, try to make Skia smarter and faster on the CPU side. On the Christmas list of API features we'd like to think about are the following. Kind of the most interesting to me, but the hardest, is to turn what we have done in terms of efficiency and cleanliness in the code to support a threaded world and find ways to extend that to a multi-process world. We're not there, but boy, we sure want to get there. We want to have effective API patterns in Skia where you do the right work in the background, and then as you draw, things are made available in another process. Some smaller ones, we haven't done sRGB yet. Sorry about that. Working on it. We have a file format for picture, which means we take our picture and we write it to disk, and with a little bit of care, we'd like to do that a little better so that you can actually have a file format that in fact is long-lived, and you might toss it around between processes or between apps, who knows. Google just recently open sourced a PDF project called PDFium. We have grand hopes to insert Skia into the bottom half of that code project so that when the PDFium top-level code parses PDFs for use for previewing or et cetera, that we can intercept that at a high level and get those drawing commands and push them into our Skia API level. And now, if we do it, you'll have PDFs that direct render to GPUs, or PDFs that turn into thread-safe pictures we can toss around. PDFs that we can send back to PDF with our printing code. Working on it. It's a big code base in PDFium. And last, we'd like to have a stable API. So we actually are starting formally to try to nail down a subset of the API that we think ought to live for a while. We're calling it a C API, but really the value here is going to be a C ABI that is stable. This work has started. We've started to write some bindings on top of it, because that's what you do once you have a C API. So we do have beginning examples of all these languages talking to Skia through this sort of stable layer. We don't know what we're going to do with it, but it's fun to start. Okay, that's the end of the talk. But as the late, great Steve Jobs says, one more thing. The slideshow you've been watching is an example of script bindings on top of a stable API. So this whole presentation is a Skia app written in Lua that talks to Skia. You can see why this text is really boring, because I didn't put any graphics in. So the C application I'm running is this app. You saw it whizzing through earlier. This is called sample app, checked into Skia. Every time, this is our grab bag of regression tests, interesting demos that draw something pretty. We throw them into this app and cycle through them. So got to have the thing. One of them is called Lua. This one. And this one says, oh, find a file with a hard-coded path name, load it in, and then talk to it through a lifecycle API that we invented, but very much would look like something inspired by Mojo, or perhaps a variation of Canvas without some of the baggage of Canvas. So here we communicate to this scripting client, and we say, okay, this is your width and height right now, and here's your drawing context. Please draw me a frame. And then when I resize the window like this, I go back to the script and say, sorry, new width, new height, do what you will. In this case, the code in the script has said, I like to present a canonical view. It computes a scale factor so that things just got smaller, but this is not imposed on the script. When I resize non-squarely, it decides to center itself. This is just the script's decision. The script does not create off-screen buffers, though it can. It does not create pictures and hand them back, though it can. In this case, it is doing a direct render into the drawing context, the C++ drawing context that I have down here, which I've wrapped into the scripting language and tossed over the fence. So it gets at, it says, okay, fine, draw, 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 comes back. When I hit a key, this sliding key, this is the script saying, okay, I drew a frame, effectively request animation frame, I need to draw again, but it doesn't pound on me. It does not sort of draw with ill-defined frame boundaries. It says, I need to draw again. I call it, I need to draw again, right? That's how we do an animation. Let me zoom it back up. So I can play little cute keys. So if you want to see text blobs in action, these are all text blobs. If I scale the text size up, you see the multiple lines creating out. So each little, you can't see the colors. Green or red hairline recs are the bounds that the text blob computed when I poured text into a rectangle. But this means that in this scripting language, we expose text blob as this nice baked immutable thing back to the scripting language. So they do their expensive labor of line breaking, positioning, whatever they need to do. We give back them a script object that says, here you go. When you want to draw that again, just give me this handle. And we go for free because, of course, behind that is a native pointer to the right thing. I can, right. So the whole thing is drawn with direct calls. I can hit a key which won't draw anything differently for you. Okay, now all the rendering from the script is in fact being poured into a picture. So now when I slide it, oh yeah, I hit another fancy key. Now I'm just playing back the picture that the script client gave me. The client, I get to play it back. So it's very fast. I don't have to talk to the script engine anymore. And I can do extra window dressing. So if you see it, I'm now using an image filter DAG, an image filter. I have to say DAG because that sounds better. And applying a blur to the world on every frame. But it's okay because since the script doesn't know if I'm software or GPU, it's agnostic. I'm in fact running on OpenGL in this whole app. So that blur is pretty fast. I get to spin it, I get to scale it. All this unbeknownst to the script. I can hit another key and pretend to be Canvas 2D, or Canvas, yes, Canvas 2D. And now, I don't know if you'll see it, it may go too fast. If you look at the initial change on clients, now what the code is saying, you know what, I don't trust this picture crap. I'm always going to make a buffer because buffers are the fast thing. So the script says, you know, with a script API, make that off-screen surface, draw into it, snapshot an image, and now I have this nice immutable image and I can animate the transformations of that. It's very fast. However, the script doesn't know the GPI because the script thought it was running at 640, 480, because that's how it likes to think about things. But I've zoomed my window to whatever this monitor is. So when I do these transitions, anyways, we end up getting a low-res version, which we smear. You know, Skia dutifully does the right thing, but it's the wrong thing. So these are all just examples of us exploring with the Mojo team, with the HTML spec guys, as Skia has evolved to have sort of a more modern sense of itself in terms of what is encapsulated, what is hidden, what is accessible, what is not. We've sort of seen an evolution of a new layer of coding patterns to use Skia. These involve pictures, modern pictures that now have these sort of thread properties, surfaces that hide the ownership of the pixels better, pipes, etc. Taking images that are agnostic, that don't know that they're textures or rasters, and trying them out in an application model to see how it flies. Jumping to the end. Okay, thanks very much.